All right, so let's go ahead and look at some of the information necessary to complete this 3A lab for finding density of an object. We're going to have a little cube that's made out of maybe foam or plastic or something, we can't really tell. And we're going to find the density of it through a couple of different methods, and we end up getting fairly consistent answers with each of them. So some of that's outlined here. It talks about how we read a graduated cylinder. It gives us some example densities of some different materials. All of these are liquids. So this is going to be slightly randomized. Different people are going to see different liquids. Everybody's going to see water. And then the other two that you see, I think, change from person to person. Interestingly, if you take the online chemistry course, as far as their Alex labs, apparently they've got another version of this lab. Not quite the same, but very similar style. Okay, so we're going to assume that the little block that we have is evidently a perfect cube. So we would think then that the length, width, and height would all be the same number. So they just rename that as edge length. And because they're all the same and there's three of them, then you can take and raise that to the third power, or you can manually multiply 3 times. And that's how we can find first the volume of the cube. Then density is mass divided by volume. So I had a teacher in high school that told us I heart density because she said if you take the M and the V and you kind of squint a little bit, that it looks like a heart. I think she even maybe like drew the arrow and put, like this, whatever. So as long as you remember, or you can look up the formula, mass divided by volume gives you density. Okay, then there's a short video that when you're in the live lab, you can watch through. It's evidently 24 seconds long, but I skipped ahead so I could show you these as notes and use my own voice to describe. But it talks about finding different masses and volumes and eventually density of a solution. So we're going to use this trick a little bit later, and we'll see that then. All right, then example densities. This is the same little table that was in the introduction page. Like I've mentioned before, you can always skip back and look there. So you've got methanol, butanol, water, ethylene glycol, diethylene glycol, and dichloroethane, or ethane, depending on where you're from. Um, some of these are less dense than water, and some of these are more dense than water. And again, you may see combinations of these depending on what your randomized version ends up looking like. All right, so some starting sort of check your information questions. I'm not going to help here, just like I never do, but make your best guess and then check and see if you got it right. If you got it wrong, read the clues, try it again. These are boxes, so not bullet points or circles. So if there are boxes, that means you can pick more than one answer. So typically there are two answers whenever you've got boxes. Okay, oops. Now, part of what that was mentioning, talking about these digital scales or balances like this, if it's not tared, T-A-R-E, tared, if it's not basically reset to zero, then your reading is going to be very slightly off. Excuse me. So this reads 0.01 grams, so there's nothing on it. Honestly, somebody should just hit that little button right there, and then it'll turn to zero, and it'll be fine. But evidently, they decided not to do that. So if you put the cube on there, excuse me, now it reads 0.94. You have to remember, though, that 0.94 has an offset, right? It didn't start at zero. So the additional mass from the cube is whatever that difference is. So it's a little less than 94. It ends up being 0.93. So minor inconvenience. It honestly wouldn't change the answer very much, but it is important to indicate these things. All right, so now we have a caliper here. So we have a bunch of them in the lab that are made by Vernier. We have some other analog ones that are slightly different style. But this gives you 3 decimal places in these measurements. So the ones that we have measure as portions of millimeters. This one might be a slightly different style. I can't read that small. But we have a measurement that we take here, and if we assume that this is a cube, then we're going to take that 0.996 or whatever you end up with, and we're going to cube it. So remember, if your calculator doesn't have a cube button or you can't find it or it's acting funny, then you can just multiply 0.996 3 times, and then that's going to give you your volume. And then remember, cube density, there's even clues in how the units work. Grams divided by centimeters cubed means we want to take our grams number here divided by our centimeters cubed number there, and that's where your volume or your density is going to come from. In case you forgot, D for density, mass divided by volume. Remember, if you kind of squint a little and draw the M and the V right, looks a little like a heart. Okay, so that's a way of using basically direct physical measurement to calculate the density of that block. Then now we're going to go through some indirect measurements, ways that we can measure technically other things and still learn about the block and eventually find a density. So in this section of the lab, we've got some chemicals, and these are the ones that I said it might be slightly randomized between different people. I think everybody has deionized water, so I think everybody has this one. But I think I had before methanol and butanol as my two different samples. And in this second time, or actually probably third time through, I had different chemicals. So not sure what you'll see, but the process is the same anyway. First, you want to read the volume on the graduated cylinder when there's nothing in there. We see that it looks like it comes right on down to 5. So we'll need to keep that in mind for decimal places later when we take official measurements. And then we want to put the block in there and see what it does. So it went from 5 up to 6. That's also a way that we can estimate the volume of this thing, but that's not a question yet. What we want to know is what happened. And so we can see that it hits the bottom of the cylinder. So it sank. And then we want to move on to the next part. That's the methanol finish. So it didn't get highlighted here, but that would be done and that's finished now. So diethylene glycol. Oh, look, now I checked it off. 5 milliliters in here. Then we're going to put the block in it, and once more. Oh, nope, I was wrong on this one. This one floats. Okay, so that also means that we can't really get a decent measurement on the volume of the block this time because it's only partially underwater. Okay, but then that's the diethylene glycol finish. And then once more, we're looking at water. So we fill up 5 milliliters of water. We are going to put the block in there, and this one floats again. Okay, so where this is going to be important is we need to find fluids that have different behaviors, because where the block sinks in this one, that means the block is more dense than the methanol. And then where it floats on the diethylene glycol and the water means that it's less dense than diethylene glycol and the water. And so we can use a combination of where the block sinks and where the block floats and eventually figure out what the density of the block is from there. So let's continue on through. That's part of what this is talking about. Again, these are boxes. That means select all that apply. So I believe there's 2 answers for each of those. All right, if you have trouble on them, if you get them wrong, read the clues, try again, and move on from there. Okay, so now we're going to finish up the scenario that I talked about a minute ago. We need to find a solution in which the block sinks so that we can indirectly measure volume, and then we already know the mass of it. We can find density from there. So we fill up. It tells us to use methanol. So remember that it sank in methanol. Fill it up between 3 and 5. I just did the maximum, went to 5. We put the cube in there and it sinks. Okay, so, and actually where it sits, you can almost kind of read the volume there, but that's not really how you do it. You want to find the difference between here where it went up to and here where it started. And because it seemed to be on those perfect lines, 5.0 milliliters, 6.0 milliliters, oh, sorry, 2 decimal places, so I can see there's more lines here. So technically, we were at 5.00 milliliters before. We went up to 6.00 milliliters before, or sorry, after. So I think it should be relatively easy to find the difference there. So that's going to tell us that our volume, again, the difference between these is 1. Then if we want density, density is mass divided by volume. So here we're going to take our mass of 0.93 divided by our volume of 1.00, which predictably just gives that number back again, because it doesn't usually do a whole lot when you divide by 1. Okay, so that was the second method. Now we're going to look at a combination of fluids. And so remember that it sank in methanol and that it floated in some of the other ones, right? So I don't want to give too much away for this question, but give it a try. It does say select all that apply. So remember that these are boxes. You'll probably have 2 answers. Technically, we would have multiple options for how we could finish the next section in the lab. Okay, from here, it's going to go ahead and choose for us the 2 methanol and water in different combinations. So remember, in methanol, the block sank, and in water, it floated. So if we could find the exact right combination of these, we can make it suspend, which would mean that it would stay somewhere in the middle of the fluid and it wouldn't sink or float. So we're going to end up just doing that a bunch of times. So following through the example, it says 2 milliliters methanol, 1 milliliter of water. So 2 plus 1 is 3, so that makes sense for the fluid level. We put the block in there, and it sinks. Okay, so not what we're looking for, so we keep going. All right, so now 2 milliliters of methanol, 2 milliliters of water, so 2 plus 2 is 4. Notice it's filled up a little higher. Then we put the block in there, yeah, and again it sinks. So not what we're looking for. We keep going. All right, now it tells us 2 milliliters of methanol, 3 milliliters of water. 2 plus 3 is 5, so we're here. We put the block in there, sinks. So yeah, not going too great so far. And you can see we've got a few more of these to try. So next one, 2 milliliters of methanol, 4 milliliters of water. So 2 plus 4 is 6. Makes sense with what we're seeing. And sinks. Okay. Well, we don't have too many more options, so we should be getting here pretty soon. We've got 2 milliliters methanol, 5 milliliters water, 2 plus 5, 7. Here we go. Put the block, and still no luck. Well, there's only one left, so I'm really hoping it's this one. So 2 milliliters methanol, 6 milliliters of water, 2 plus 6 is 8. We're even at this point getting close to the maximum volume on our graduated cylinder. We put the block in, and success. So it floats. Or rather, I'm wrong. I'm sorry. It suspends. So float would mean truly on the top. Sink means truly on the bottom. Suspend means somewhere in the middle. So you could push this slightly further down, and it may hover or bounce a little bit, but it's going to stay somewhere in this fluid as long as it's reasonably well mixed. So there we go. And then we can use that information, and we can actually calculate the density of the cube. So we would need to go back to these densities. So methanol, that one, 0.7918, and then the water is 1. So 0.7918, I'm trying to remember, 0.7918. So methanol here, 2 times 0.7198. Oh, sorry, I had these written down and I lost my paper. 7918. I knew that was wrong. I wrote it down and it didn't feel right. All right, let's fix it. 7918. And then the water is density of 1. So what we're doing is we're working back here so we can find the total mass of our stuff. And we're going to divide by our total amount of fluid, which is 8 milliliters. And that's how we find grams per milliliter. Okay, so 2 times this number, basically just plus 6, because that's multiplied by 1, will give us some value. I'm not going to tell you what that is because I want to leave some work for you to finish. Then once you have that value, you're going to take those and divide by 8, right? And then you're going to have grams from these calculations, milliliters from the 8 milliliters total, and there's your grams per milliliter. And then that's it. So success, we've got congratulations. Hopefully you've got one of those too because you finished. You'll have some lower score if you ran out of time or hit the due date or submitted early and skipped things, but hopefully you got to here. All right, so that's it.